Just before we get started on the review, I posted the exam and I was going over the exam and it dawned on me there are a couple of reactions that I guess I skipped over that I think are worth it for you guys to certainly know. This is going back a little bit. This is just going back to the aromatic chemistry. So I'm just going to spend probably 10 minutes just exposing you guys to a few reactions that I guess I forgot to go over, and just sort of we'll discuss them, why they're important, why I think they're important, just so you guys can know what to expect from them. And the first one, so the first one has to do with protecting groups, right? So what we're going to refer to here is primarily benzylic position. So in the past, we've heard about like this position, right? The position that's adjacent to a alkene, right, as allylic, right? We've said that in the past, right? This is allylic. And in the same way, say for example, the methylene, if you will, that's next to a benzyl group that's in conjugation with that is called benzylic. And we know that there's some differences, right, in terms of how these would behave compared to, say, for example, a standard methylene group, right? So, for example, we learned about under the radical chemistry chapter that you guys took last semester, right? You learned about, for example, allylic bromination, right? Where if you take, say, for example, this talk's fine as long as I get the top end of it. All right, because, sorry, learning how to use this chalk. All right, so if you have, say, an allylic proton on a molecule, as you guys have sort of learned, one of the things that you can do is through sort of radical-based processes, you can actually brominate that position. And so usually what you'll do is you'll use something like NBS and some type of radical initiator, right? So it's an allylic source of bromide called NBS, right? So you'll take this and you'll have some type of a radical initiator, whether that's light or, say, for example, a peroxide. We'll stick with what the book says, which is benzoyl peroxide. You can do it with light, you can do it with whatever. The idea is that it's a radical-based process, though. And so what's going to happen, right, is that this bond right here, in this case, is actually pretty weak, homolytically, meaning that it can fragment really easily to generate oxygen radicals. So oftentimes, initiating processes in radical chemistry involves what we call weak homolytic bonds, things that can break just thermally. You can heat them up a little bit, you can fragment them, they'll generate radicals, and then you'll set off those radical cascades that it's probably been a while since we talked about, right? And so the idea in a process like this, right, is that once you can get to that radical, once you can get to something like that sort of O dot, you can now begin to start setting off cascade processes, okay? And one of the radical cascade processes that you can do, sometimes you can do these with things, like we saw this a little bit, I think, with anti-Markovnikov bromination, right, of, say, for example, alkenes, where it reacted with HBr, generating a Br radical, which added to the alkene, right? So we saw that in the past. In this case, what you've got is a methylene group there, which, if you can extract that, again, it's going to be a reversible. Have these arrows going through this. What you can get to now is a radical, right? And you guys know, you've seen in the past, right? Whether it's a carbonyl here, or whether it's an alkene or an aromatic group, right? In these instances, what can sometimes happen is you have the stabilizing factor. So they can both stabilize negative charges, they can stabilize positive charges, effectively through resonance stabilization. And so in this case, you certainly have that ability as well, right? Say, for example, stabilize that radical, in a situation like that, right? In the case of NBS, what you now have is a molecule that it can in principle react with. Okay? And so, you know, how this sort of takes place at this point, you can just sort of imagine. And there could be other mechanisms that you could imagine drawing with this, but at least this will hopefully make sense to you guys, right? Is that now you're going to put a radical on nitrogen and effectively, and again, it could go to either side, and you could perhaps predict which way it might go based on the other side. But that's the general idea, right? Is you've seen in the past you can do this reaction, sort of a little bromination, right? So you can begin to brominate at that position selectively. You could probably imagine that benzylic positions would do the same thing, right? So that's really the only point that I wanted to make here is that if you take a benzyl group and you want to say, for example, functionalize, right? Let's say, for example, you want to make a molecule that looks something like this, right? Benzyl bromide. And say, for example, you were starting from benzene, right? You could probably make this in a couple steps using this type of approach, right? Because if you took the benzene, you methylated it using a Friedel-Crafts alkylation, right, to make toluene, and then you could simply take, for example, you basically take toluene and using these conditions, right, NBS, and again, whatever you want, radical initiator. Right, so it could be this, the ROOR is fine, right? So some type of radical initiating process, so light, whatever, will get you to that compound. So again, this could be useful. It would be selective for that bond. If you have a whole bunch of different, say, for example, CH2 groups around, you could imagine selectively brominating that CH bond, and obviously in, say, for example, synthesis in particular, right, you guys might find value in this, right, because being able to put a halogen in a position, now you've got a handle, right, that you can convert it into a Grignard to make it into a nucleophile. You can treat it with an electrophile to add something else there. So you can imagine a lot of versatility here, and especially within synthesis of aromatic compounds. Again, there's no direct way that we know of to say get from benzene to here, but you guys should all at this point be able to make this from benzene, right? Just using Friedel-Crafts alkylation, bromomethane, FeBr3, right? You can make this, and then you can subsequently convert that to the allyl bromide and further functionalize that. So that could be very useful in your synthesis. So again, know that reaction. And the only other one that I'm going to show you guys, actually I'm going to show you two more. Another thing about benzyl groups is that, I definitely discussed this last semester. I might have skipped over. Did I talk about benzyl protecting groups? So another sort of benzylic advantage that you could potentially use in synthesis in the past, right? We saw examples where if you had an alcohol, right, and you wanted to do some other chemistry, but that alcohol was going to give it problems, right? Whether it was, say, adding a Grignard to a carbonyl nearby or something else like that, we would want to protect the alcohol, right? And one of the ways that we would do that, and that you guys learned, was how? So you could put an acetate and an acetyl group on it, but that would probably react with a Grignard, right? TMS, so that would be one possible group. Another group would be a TMS, right, or a TRS. So TMS, whatever. I usually just say TRS because truthfully, there's like a ton of these TRs, meaning some alkyl group. So trimethyl people generally don't use trimethyl because you can sneeze at it and it will fall off. But there's certainly other ones, TBS. So just TRS, just to say there would be some type of group. And again, usually in this case, you have some type of base like triethylamine. So what you've done here is you've silated this compound. You can do other chemistry. It's somewhat acid, there's mild acid, not too bad, you can take them off under harsh acidic conditions, pretty stable to base conditions. But then when you want to go back, you guys learned that you can treat this with effectively a fluoride source, right? And the idea here is that what this is, just as a reminder, what this TRS is the silicon-oxygen bond. And there's a lot of different sort of fluoride sources. So we'll just say F minus for the time being, but there's a lot of different sources of fluoride that we can use. Sometimes people will use HF, sometimes people will use a reagent known as tetrabutyl ammonium fluoride. But again, for the sake of this, you know, just fluoride minus source. What happens in this case is that the fluoride silica bond is very strong, so you can just think about it as it's going to want to make this bond with the silica, it's going to make the bond with the silicon oxygen is going to break, and it's going to go back in the reverse direction, okay? So this is just a reminder of siloprotecting groups, and the important thing here is that the benzyl, you can actually do benzyl protecting groups as well. So, again, we just learned how to make benzyl bromide, for example. So if you take this molecule and treat it with, first deprotonate it with something like sodium hydride or sodium metal, right? So you make the alkoxide and then treat it with subsequently the benzyl bromide, right? You're going to make the oxygen-carbon bond, kick off the bromide, and you're going to effectively protect this group as a benzyl group, okay? And so this benzyl group will behave for a while. You can carry it through a bunch of different steps. And much the same way that fluoride, you don't see fluoride that much, like as a reagent for other reactions. It's sort of a more rare reagent, and that's one of the reasons why PBS is valuable, right? You take it off under fluoride sources, usually other things will be fine. In the case of a benzyl protecting group, there's actually quite a few different ways that you can take these off. There's actually different derivatives of these, for example, that can come off under different conditions. We discussed this a little bit about changing substituents on here can change the effect of the benzyl group here. But one of the most common ways, and what you guys might want to know, is that if you take this molecule and you want to debenzylate it, what you can actually do, and I'm not quite sure of the mechanism of this, per se. I've convinced myself of the mechanism. I'm not quite sure that that mechanism that I've come up with is accurate, and I've looked for information behind this. But the idea here is that if you take this molecule, you can actually reduce it off under palladium and hydrogen. And back when I was sort of studying this chemistry, the byproduct in this process is certainly just adding hydrogen across those two bonds. You might be able to imagine a mechanism whereby, for example, you could reduce a double bond, and then, say, for example, so if you, say, for example, reduce one of these double bonds first in the benzene group, again, if you did something like this, then what can happen is that you can imagine a sort of a protonation elimination process, followed by rearomatization of that as well. I'm not sure which of those two mechanisms it really is, but for the sake of simplifying things, you guys can sort of just think about it as adding hydrogen across that oxygen-carbon bond, even though it might be a little bit more complicated than that. So again, this is often how I've sort of thought about it, but I've also seen that you can reduce benzyl groups in the presence of groups that would also, I would think, reduce faster than aromatic groups. So I don't think it's as simple as that. But anyway, so just again, another protecting group option. You can certainly imagine that sometimes you might have, say, for example, two alcohols in a synthesis, right? And you might want to protect one as one group and protect the other as a different group, so that at some time during your synthesis you could selectively remove one over the other. So there could be value, for example, in having orthogonal protecting groups, right? So you can have one alcohol protected as one thing, have another alcohol protected as another thing, and then selectively remove one alcohol so that you can play around with that. So that could also be useful within synthesis, and I think that's worth sharing as well. One more reaction, and then we'll start talking about reviews.
How do you deal with symmetrical patterns?
Let me show you, and then you can ask that question. Or maybe it's better that we talk afterwards. Because I can go off on a huge tangent with that question. And the last reaction is one that's just kind of interesting. This is actually a reaction I didn't know about before I started teaching this course. Or at least I had seen it and was kind of surprised because people don't usually do this that much. But again, this is something sort of special about these benzyl groups here. And I knew that you can take, like, say for example, you can oxidize allylic and benzylic hydrogen bonds to, say for example, a carbon-oxygen bond. So I knew that you could take a molecule like this to a carbon-oxygen bond. And so I pretty much assumed under oxidative conditions. So I knew that if you took a molecule like this and you treat it with, say for example, Jones reagent, what can happen, is you can actually oxidize all the way up to benzoic acid. What's that? The specific conditions for it, maybe, to be able to start getting to radicals. I'm not quite sure. I believe that under the conditions that I was more familiar with, it uses like samarium, selenium, what's that? Yeah, so my bet is that it's certainly a rate issue, right? I think that this would certainly be a more forcing condition, and you could perhaps imagine that. Whether it's simply refluxing is going to suddenly do one versus the other, it would likely just be a game of rates. And so yeah, that would be a little bit more difficult to oxidize. So maybe you can imagine that you could play with that. So this is a slower process. What I thought was kind of crazy, so I knew this. What I didn't know until I was teaching this course is that apparently, if you have even like two alkyl groups there, and you treat this under the same conditions, you get the same product. And this is kind of bizarre. Again, I don't think this is generally a strategy that's used, but it's kind of interesting, right? And it turns out as long as you have at least one proton at this position, you will oxidize alkyl groups to the benzoic acid. So if there is just that one stabilized carbon, then you can get to the carbon-oxygen bond. And then once you get to the carbon-oxygen bond, then you can actually begin to oxidize carbon-hydrogen bonds. Yes? So was sp2 hybridized? No. Right. I wouldn't expect it to. In fact, yeah, because radical stabilization, you should sort of, and likely the mechanism is probably going through some sort of pseudo-radical. I could actually draw other mechanisms that could get there, but, you know, based on what we were talking about earlier, you can at least relate it to radical-based processes. And in that line, radicals are, you consider radicals electronically poor, right? Because they don't have a full octet. And so in that way, when you're talking about relative stability, you compare them to carbocations, right? So you can sort of make that same trend. So in that same way, an sp3 sp3 carbocation is more stable than sp2 carbocation. An sp3 radical would be more stable than sp2 radical. So that should sort of answer that one. So anyway, so this is just some of the interesting things. Again, taking this to the next step, right? The point is if you have no proton there, it's no reaction. So you sort of at least need one proton. So anyways, I'd asked a question like this on the exam, and that jogged my memory of the fact that I had not discussed this semester. So. Okay, so just those are three reactions. Put them back in your in your back pocket. I think specifically, I'm not sure that this one's going to be all that potentially useful for you, unless, say, for example, you want to get a carboxylic acid like a benzoic acid. This could potentially be valuable. Specifically those others, like making benzyl bromides, I think could be really beneficial and could be something you guys want to use in a synthesis. And I think having those two different protecting groups, you guys could also potentially find value in. So I think those are three reactions that could definitely be useful for you. And there's some others in that chapter, like the quinone synthesis and stuff, but I'm not. That's fine. Okay. All right. So with that. I spent a little bit more time than I wanted to, but let me open the floor to questions, because this is the pre-exam, I guess, review class. Would you like me to go over a certain type of problem? We can start with that. Yeah. Okay, which one though? The palladium catalyzed ones? Which one? Stili. Yeah, so the palladium catalyzed. Okay, so, and specifically, what do you want me to go over about that? You just want me to quickly refresh it? Okay, so just as a quick reminder, again, you can go back and watch this video, so I'll try to not just repeat what I said previously, because you can obviously just go back and watch those videos. But just as a reminder, what we have here is a very powerful method, right, where you can take an alkyl halide, like an alkyl bromide, and an alkyl metal, right, and under palladium-assisted processes, palladium catalysis, what you can get to is a carbon-carbon bond, right? And the only difference with a Stili, right, and so we've learned really, well, in terms of this specific thing, we've learned two versions. I'm not going to include the Heck or the Sonic Shear, which are a little bit different. But in terms of this basic process, we learned two reactions. One was the Stili, the other was the Suzuki. The difference in these cases, right, is that in the Stili, the M is tin, usually something like tributyl tin or trimethyl tin, right? That's the sort of metal source there. In the case of the Suzuki, the metal equals a boronic ester usually, okay? But again, when we think about these in terms of the chemistry behind it, is this an electrophile or a nucleophile? It's an electrophile. So if this is an electrophile, a lot of times this is thought of as a nucleophile, right? You might imagine a scenario where the tin carbon bond, and certainly tin carbon bonds are very nucleophilic in nature, right? You've seen those instances in the past where carbon metal bonds are nucleophilic, right? We saw it with metal, with carbon copper, we saw it with carbon magnesium, we saw it with carbon lithium, for example. So that should be fairly straightforward. The interesting difference here, though, is in this case we have a boron, right? And boron is inherently electronically poor, so if anything, it's going to want to be pulling electrons away from the system in general. So just having a boron there is not going to be nucleophilic enough. And so one of the differences between these two is that in the case of the Suzuki, what you need to use is you need to use a aqueous sometimes environment or some type of a basic environment, so you need some type of a decent nucleophile, like sodium hydroxide or sodium methoxide or something like that. And what happens is that converts it, we'll just say OR minus, even though it's actually always generally goes through the boronic acid, so usually you have other components to it. But just to sort of make the analogy, the active sort of coupling partner in the Suzuki is going to be the boronate, B minus. So that's one of the ways that you can sort of remember the differences between the two. So the conditions vary slightly. There's advantages to some. Again, boron is a lot cheaper. Boron is a lot safer. It's a lot less toxic. But you do have to use these nucleophilic conditions that sometimes other things might not survive in. Tin, on the other hand, is already kind of activated. And so usually what people will do is they'll try the Suzuki first, unless they already see something that they assume won't work. In these cases, they'll often try Suzuki first. If the Suzuki doesn't work, then they'll move to Stili. And so that's this chemistry. No, the catalytic cycle, yeah. What word? Well, what cases? Well, in instances where there could be reactive, where things could react with sodium hydroxide, right? So You know, maybe you have an ester, right? And you've got to use sodium hydroxide, and maybe the ester will hydrolyze with the sodium hydroxide around. Maybe, you know, that's one example. Maybe you have a halogen, another halogen nearby. Maybe this halogen here, even for example, might undergo facile elimination for some reason, right? So, so just, yeah, just basic conditions that or some structural components on them wouldn't necessarily survive that. Okay. So know this again. The mechanism, right? Know the mechanism. Again, go back and rewatch the video. You know, but again, it involves a 3-step process, which is effectively you insert, right? You start with palladium 0. You insert in between these bonds. Then effectively, you can think about this almost serving as a nucleophile and displacing the halogen from the palladium if you want, and that would be called the transmetallation, which again, you could draw it that way just because it might be consistent with what you've seen. It's not quite that. Followed by a reductive elimination at the end, which would bring those two together and regenerate palladium 0. So it is a catalytic process. And again, both these are the same in that extent, just the difference being the metals. Okay?
So is that reaction? I'm not saying
this one?
no, this is the mechanism.
Oh, the mechanism is this.
No, the mechanism is that.
Oh, just complete this? Complete my thought here? Yeah, so again, this is my not quite mechanism, but could be the mechanism, right? So the idea is that once you de-aromatize, you might have a fairly acidic proton here that might just eliminate, you know, you probably protonate that, eliminate. And then once you get here, this is just a tautomerization away from toluene.
You get hydrogen gas
Palladium, yeah, so it's palladium and hydrogen. This is the hydrogen. I was saying it was if it was reduced. I was just giving an alternative mechanism. Yeah, don't drive yourself nuts. Just like I said, you could think about it as just adding hydrogen across that carbon-oxygen bond, going directly to here and DOH. But again, you could also, if you're like, I don't really like that, you could also imagine invoking a mechanism where you add one equivalent of hydrogen to this benzene group and do an elimination. I don't think it goes through this mechanism though, but this is one of the ways that when I was first learning this chemistry, this is one of the ways that I first convinced myself that hydrogen would debenzylate a group. But subsequently, I've seen lots of examples where compounds that would ordinarily seem to be untouched by these are reduced off. So I'm not quite sure what the mechanism is. I'm not sure that it's 100% known. So, okay. All right, other questions? Yeah. April Fools. Yeah, just pass out the exam, right? Yeah. Here's the exam that's coming up, guys, for those of you who showed up. No. All right. Any other specific questions about specific topics? I could. So let's discuss that, just because I think that could be sort of brought up in the context of the synthesis problem, right? If, you know, I mean, I'm trying to think scenarios where you might have that, but let's say that you were in a situation where you had right? I mean, if you had, say, for example, symmetric diol, like a molecule like this, there is nothing that you're going to be able to do that is going to be able to selectively protect one group over the other without some type of chiral control, right? So because what these two oxygens are prochiral effectively. If you change one of them, the molecule becomes chiral. If you change the other one, the molecule also becoms chiral, but it's the opposite enantiomer. So actually, when I was a graduate student, a friend of mine developed a catalyst that was able to selectively silate one of these over the other. It was a chiral catalyst. It was a big paper, I think, in like Nature or Science, one of the big journals. For years, people have desymmetrized based upon enzymes, doing acylation chemistry to draw as much as possible protective group. So enzymes can do this, but absent from anything else like that, the best case that you could likely do is hope that if you have some big and bulky solid group that somehow once you put a big solid group on one, it might slow down the other, in which case you wouldn't get chiral stuff, but you might get monosilation. Now, if it's not necessarily symmetric, if it's, say, for example, something like this, right? Say, for example, you have non-symmetric diols, where there could actually be differences in the chemistry, then you can certainly protect one over the others. And you guys might be able to even predict how you might do one over the other, right? And so if this were the case, if you wanted to protect one of these over the other, how might you protect, say, for example, this one selectively? We'll start with this one, maybe a little bit easier. Some bigger nucleophile, right? So if you wanted to silate this, right, and you use, say, for example, TDS chloride and triethylamine, right, you would expect that you got a big, bulky group, TDS, that's going to protect there because this is going to be very sterically hindered. In fact, you can up that selectivity using Lewis base catalysts. So, especially, did you guys learn about DMAP ever? Dimethylaminopuridine? So this is a Lewis base catalyst called dimethylaminopuridine. Okay? And actually what can happen is this will activate the silyl group by attacking this first. And now you actually have an even bigger electrophile, and you can actually get even greater selectivity based upon Lewis base catalyst. So certainly you could imagine, and again, you would need to invoke this. I think that you guys could basically say, I believe I can protect this one first over this one because this is sterically bulky or something like that, right? But what if you wanted to go after the other one? It might be a little bit more challenging, but let's sort of think about it. How might you, like, so, how might we get, say, OPG, some protecting group? Right? How might we get this compound? Yeah. Well, yeah, you were going actually to one strategy, so which was the same idea. You could also just silate it, right? So what? What is it? Esom? Esom. So what Esam's saying is that you can actually oxidize this, because you can't oxidize this one, so that's pretty clever, right? Oxidize that to the aldehyde, put the TDS group over here, right, and then reduce it. So that's brilliant, yeah. So that's one way that you can do it, right? If you don't care about the nature of the protecting group, right, you could even go through the silyl group, right? You could silyl protect and do that same sort of thing. Silyl protect the one. You could say, for example, put on a benzyl group, and then take off the silyl group, and maybe get an O-benzyl group here. But if you wanted to go selectively and do it in a single step, this might be a little bit more challenging, right? You can't necessarily rely upon sterics. You can't rely upon sterics. Well, sterics and sterics often go hand in hand. But if you don't rely on sterics, within chemistry, there's really two effects. There's sterics, and there is the other one. What's the other one? What's that? Yeah, electronics. Say it loud and proud, right? Electronics, right? So there could be electronic effects. And what are some of the differences, say, for example, between this alcohol that we might be able to use electronic effects to actually put something on here? What's that? Yeah, you might be able to say, for example, I have no idea, I'm just guessing here, but what if, say, for example, we wanted to print it as an acetate group? You know, might we invoke a mechanism where we, under mild acidic conditions, right, and say acetic acid with a little bit of other acid in there, perhaps we protonate this one, right, and then you're going to lose the carbocation in the presence of acetic acid, that acetic acid might add there, right, so maybe acetic acid, maybe trace catalytic another acid. Right? I mean, I don't know. You could certainly imagine other mechanisms that would also acylate this other side, right? So I have no idea, that's what I'm saying, I have no idea if this would work or not, but you could imagine a system where you might be able to play on those electronics to have a tertiary carbocation, and if you're trying to protect via SN1 chemistry, right, so that's really what you're trying to do is leverage the fact that this is going to undergo SN1 chemistry, right, and hopefully something like this would drive the acylation before, say, for example, transesterification or something like that over here. So I have no idea if this would work or not, but you could propose that something like that might be able to take place. Okay? Okay, so there's the diol question. Yeah? The Meisenheimer. Okay. So I mean, the Meisenheimer is, we're just speaking about, in general, benzylation, or sorry, arylation, right? We're just talking about, in what context? I'm not really sure, right? I mean, Meisenheimer complexes, effectively, we've discussed this, really anytime you treat a molecule, in principle, with an E+, right, you are going to get the Meisenheimer complex. And depending upon what the groups are, I'm trying to remember exactly the Meisenheimer deals with this. Yeah, just give me 2 seconds. I just got to revisit Meisenheimer. Because it's related. It's directly related to everything that we've discussed in the past in terms of orthopara directing and things like that. Meisenheimer. $927? I mean, because the Meisenheimer, it's been a while since I've thought of Meisenheimer, but it refers to a specific substitution pattern, if I believe. We haven't really brought it up, that term, but I think for the sake of this course, what's that? Yeah, I mean, it's just a matter of the stabilization of the carbocation based upon where you're going to approximate something. So when we have, say, for example, a methyl group there, it's basically effectively what donates things, I believe, orthopara. Again, I don't remember the specifics behind if there are more specific aspects of that. Right, so again, it's this idea that I believe, it's like what we've sort of talked about previously, that if you have a charge, when you react with a certain group, the selectivity that you're going to get is going to be effectively based upon where you can resonate and have a better resonance form of that positive charge. The way that we sort of taught it, yeah. Hold on. It's MEI, right? Well, it wasn't on that. Oh, there we go. 947. Let me just see what the book says. Oh, so yeah, so it's. Oh, yeah, I mean, okay. Yeah, so again, okay. So we discussed a little bit about, so we discussed previously, right, Michael addition. This is how, you can give it a name and then you can sort of try to remember it based upon that name. I obviously didn't remember the name and what it meant because I obviously remembered it in a completely different way. The Meisenheimer complex in and of itself is effectively what I was trying to describe in my past class, which is when you take a look at something like, say, for example, a nucleophilic aromatic substitution, formally what it has to be, and you can sort of treat it that way, is like a Michael addition, right? Like a 1,4 addition into an ester, a vinyl nitro, anything where you're going to be able to stabilize that negative group into that resonance form, right? So when you add 1,4 into a species, right, whether the alkene is just part of, say, for example, an isolated double bond in conjugation, or when it is, say, for example, embedded within a benzyl ring, right, you will formally need to add to a position where you can resonate into that bond, right? And that's, I guess, formally they're talking about it in terms of nitro in the figure when they're bringing up the Meisenheimer complex. So really, there's only two positions, well, three positions that you could add this way. There's one position there, right? Because that's going to go up that way. There's this position here, again, because you can go all the way up. And again, depending on how we draw it, we can go all the way around the ring if we want to, but there could be that position as well, right? And so this is why in nucleophilic aromatic substitution, yeah.
Can you do that with the Gilman on benzene and nitro groups or something like that?
You don't need to with a Gilman. Because formally what electrophilic aromatic substitution relies upon, nucleophilic aromatic substitution relies upon, right, is that you need to have some type of a leaving group, right? So if you don't have a leaving group, then you can't really do the nucleophilic aromatic substitution. It'll add in, and then it'll probably just kick itself back out, right? So all these positions that I've said here, in their current form, you're not just going to add there and do anything. You need a leaving group. But that's my point, right? But that's my point. That's my point, is that, say, for example, if you had a Gilman, right, how does a Gilman work? A Gilman works much the same way, right? We've learned that Gilman reactions, you would do it, but it wouldn't necessarily be because of this type of substitution. If you had a chloride, say, for example, somewhere else on that ring, right, because that's basically what this is saying, is that there are effectively, when you have an electron withdrawing group, there are basically three positions. There's the sort of ortho positions and there's the para position that in principle you can add a nucleophile to. So if I had a molecule that was, say for example, that chloride there, I wouldn't be able to do nucleophilic aromatic substitution with it. But I could with a Gilman, that's my point. Is that you could do this with a Gilman. A Gilman, it wouldn't matter where it was, because a Gilman works via a different mechanism. So Gilman, you don't need to take advantage of nucleophilic aromatic substitution. Now, you could in principle imagine scenarios, right, on the flip side though, where, say for example, you have two chlorides, right, on this molecule. In this case, this is ortho, right, and so you can make that resonance form, or if you want to, I guess, the Meisenheimer complex, you can add there, right, and then it's going to come back out and kick out the chloride. So you could add a nucleophile here selectively over here. I would think that with a Gilman, you might be able to, I'm not sure if there would be any selectivity to it. But I would imagine that you're going to have a tough time with selectivity on a Gilman, just because, yes, we've seen Gilmans add 1,4, but we also know that Gilmans, I'd like to think about the Gilman much mechanistically like we thought about palladium catalyzed cross couplings type transformations, in that it's not really, you can think about it like a soft nucleophile, it's more transition metal carbon bond, and it's not, I don't think about a Gilman in the same way that I think about some of these others. So I would bet that you would get a mixture in this case, if that makes sense. And again, that's the reason why Gilman works in instances where we've seen others not. You can take a vinyl halide, an sp2 halide, and a Gilman will work with it, right? And it's because it's not your standard nucleophile.
added to a benzene is just an electron withdrawal, just a carbon attached to it. Would that wouldn't do any kind of microlite chemistry with that?
Oh, like an enolate?
No, let's say you have a bit of benzene, right?
Yes.
Let's say a nitrogen.
Yes.
You just treated that with a Gilman reagent.
Right.
Or the Gilman added in like
What would probably happen is the Gilman would add in. I'm not sure completely, but my assumption would be that if the Gilman added in, that's an interesting question. It's an interesting question. I'm not sure. Because what would happen is, what would you eliminate? Right? You'd have to regenerate aromaticity. You'd likely want to regenerate aromaticity at some point. So I don't know the answer to that, actually. It's a good question. You could have, and I don't want to go too far off base, given this is a review class. But yeah, why don't you look into that and let me know, because I would think that, I don't know. But you could imagine if you could do some pretty cool things.
Yeah.
But you wouldn't be able, it wouldn't just be your standard electrophilic aromatic substitution,
Yeah.
right? You wouldn't just kick out a hydride, right? It would have to add in, and then once you add it in, something else would have to happen afterwards, if something else would happen. Say this. All right, other questions. So again, I guess that's, when we're talking about Meisenheimer, that's the extent. It's just the rationale, that resonance-based rationale that I gave you guys previously about how you need to have that in the same way this sort of Michael donation. So I compared it to the Michael, I guess that's the name. Yes? Just sort of for stereochemistry purposes?
Yeah.
Yes. Okay, so the question is, what's the product? And so there's really multiple sort of steps that you should sort of take here. The first question is regioselectivity, right? And so at the get-go, how do we decide the sort of regioselectivity in a Diels-Alder? What do we try to identify? Right, where's the delta positive? Where's the delta minus? The other thing we may want to consider is, when we draw this, what is the, well, the resonance forms, but I think somebody else was kind of S-cis, somebody was saying S-cis, right? So you want to rotate around that bond, right? So when we think about this, all right, it's good to sort of draw it. Right? And the question becomes, at the beginning, which rejoins are we get? Are we going to Diels-Alder where it reacts 4 plus 2 with this one? Or are we going to get the Diels-Alder where it reacts 4 plus 2 with this one? And so again, the first thing that we want to do is identify the delta positive and the delta minus. Hopefully by this point, maybe the alkenes should be fairly easy to identify. right? Where's the delta positive when you've got a carbonyl? The beta position, right? We were just talking about 1,4 addition, right? And that's because there's a delta positive here. So we know that there's, in this case, there's a delta positive here, which would mean that there's a delta negative there. In this case, the delta minus is here, and the delta positive is here. And so now we have to sort of identify this one. So we can start by looking at the resonance, but sometimes students can often sort of get to the resonance forms just based upon sort of pushing the electrons through the system, right? Like if you look at a molecule like this, sometimes what you can sort of see is I've got these lone pairs here, right? And I'm kind of doing the same thing just a little bit differently, and sometimes it's a little bit faster, but I can put a negative charge at that carbon, right? Just by pushing the electrons there, right? That effectively is a resonance form going right to that resonance form where you got a negative charge at that carbon. Right, exactly. And that's the question, is that you have another lone pair, and the sort of question is that nitrogen good? You know, is there another way that the nitrogen could perhaps going electrons into this? But in this case, as was just sort of brought up, it is kind of complementary in nature, because what you can do, right, is that nitrogen can just help further stabilize this resonance form by pushing electrons up into the oxygen. So you effectively have a couple resonance forms here where the nitrogen and oxygen can both help share this sort of charged system. So certainly in this case, what you're going to have is a delta minus here and a delta positive here. And again, if you're still not sure, you can always draw the opposite resonance form as well, right? And sort of ask yourself the same question, will it still, you know, does it look as good as that, right? Right there, because sometimes when you're you start to see these patterns and stuff like this, so you can get a little bit quicker at it. But certainly if I tried to draw, say, for example, the opposite, right, where, say, for example, I have a negative charge here and a positive charge here, and an oxygen, right? Yeah, so now I have a positive charge here and a negative charge up here. Drawing all the bonds just so that we have everything there, right? And so we're not missing anything. But you can see now in this case, right? Now we've got this lone pair next to that nitrogen. You know, it's not really helping us in that same way, right? This oxygen, you know, there's just that same type of resonance stabilization doesn't exist. There's not necessarily anything that screams, oh, this is horrible, except for maybe lone pair repulsion, maybe, if you want to make that argument, but that's not really something we can spell. So anyway, so this would be likely how we would have it. So the product that we're going to generate, right, would be from these two, right, where we match up the negative and positive. So that's the first step, right? And so for starting point, you can just, you know, when you're starting this, you just ignore the stereochemistry just so that you have the bonds in the right place, right? That's the first part of the question is, where is everything in relationship to everything else? And so this is now the product. And now we have to ask the question about the stereochemistry that the product would have. And in this case, we have two stereoisomers. Sorry, excuse me, we have two stereocenters. Right? We have the one here and the one here, right? And from an asymmetric standpoint, it's not going to matter whether we get, you know, we're not going to get a single enantiomer in this process. But those could either be going opposite or in the same phase, and those would be diastereomers. And so the question is, which of those two are we going to get? Are we going to get the ones where they're both, say, for example, pointing towards you or pointing away from you? Again, those are just enantiomers. Or is it going to be the, you know, what's that? Well, so that's the question that we have to ask, right? So, now let's move on to the next one. Have you done it already? Yeah. Okay. So, now that you guys have this, now the question becomes sort of, what is its relationship? And so, at this point now, you have to consider the endo rule, right? And again, this is where we ask the question sort of, what is the endo rule, right? Where does the endo rule come from? Why do Diels-Alder reactions tend to exist in this form that has the endo rule? And again, there's lots of different ways that you can sort of think about this. But I really like this, again, I learned it last semester, I really like this box method, because I think drawing in 3 dimensions is not something that you guys, with probably a few exceptions of the artists in the room, few of you guys are probably that good at drawing things in 3 dimensions, but the one thing that we can all do is draw a 3-dimensional box, right? And so at least we have something to start from, right? And so if we draw our box, right? Start with our box. And again, the idea in this box is then what we can do is we can start to draw. Now I'll use the yellow chalk, right? Now we can start to sort of look at the molecule, right? So Diels-Alder that we're going to have, right, is going to be this Diels-Alder here, where we have the diene, right, making a bond with that alkene, right? And when we think about this molecule, so we have this drawn up here, we can start with, just pick one and well, I guess we'll have to pick the one that we can't really change that much, right? This diene has to be like this diene, right? So at, say, for example, this carbon here, we have our carbon-nitrogen bond, right? Now, where is that carbon-nitrogen bond going, as is currently constructed? Is it going into the board, or is it coming out of the board? It's going into the board, right? Because this is a trans bond. This is trans, right? So we want this to be trans. And sometimes it can be helpful to even draw the proton as well, just so that we have that there as a sort of reference point, right? We don't have anything on this one except the 2 protons, and over here we have our 2 SO. Okay. All right, so that's the top part. Now what we have to deal with is again, this is the bond that we're making. Right, at this point now we're going to be dealing with the carbonyl, right? And the endo versus exo rule really has to do with whether or not the carbonyl is coming this way. Again, we have 2 options. It can either be going that way, or it can be going that way, right? And what we learned about the endo rule, right, is that when you have this ability to have this secondary orbital interaction, right, when you have a group like an ester that has pi orbital characteristic to it, it will go towards the pi bond. And we can think about this in a few different ways, right? But you can actually even draw a more extreme version where that's sitting back in there. But what you have here, right, is this pi bond, which can interact there. And that's the favorable interaction. We can actually rotate around that and actually show 2 of them as well. But this will hopefully just simplify things. And so this is what helps the endo selectivity. But did I draw that backwards? I did. Here, so it's actually these 2 that are overlapping with one another. Okay, so there's our ester again, and there's the bond, right? I just drew the wrong regioisomer previously, okay? And so there's our hydrogen, right? And so what's going to happen here is this is how the bonds are going to form, yeah?
I don't think it's management, but I think that O would be better off if it was associated with the other. Because then the O and stuff has to be
Well, that's what I was saying earlier. We could do it in either way, and the question is, yeah, so we could have drawn it the other way as well. So we could have this carbonyl there. That's what I was saying. You could have a second one as well. So that's what I was saying earlier. But in this case, now what we have, right, is the stereocenters, and the ones that we care about the most, right, is this stereocenter and this stereocenter. So that's really where we're going to be focused, right? And it's going to be the relationship between those 2. So what we're really focused on is the relationship between the groups that are here. And when we draw this product, one of the things that I often suggest to you guys is incremental steps, right? Draw, especially when you're trying to draw something new, don't try to go immediately to the final product, right? That can come with time, But especially at the beginning, you should just sort of draw what changes. And when we do the Diels-Alder reaction here, what changes? The electrons, that's the first thing, right? So what we can do is effectively draw the exact same thing. Right, with our double bond there, our TVSO out here, right? Here what we have, right, is coming towards us. We have the hydrogen going away from us. This bond, if it helps us, right, sometimes drawing it with the dashes and wedges can sometimes help as well, right? So since that nitrogen is kind of going away, if it helps, we can, if it's sort of ambiguous, we can have that nitrogen going away. We can draw those dashes, so at least it helps us visualize that a little bit more. And then what we're dealing with here, right, is these two groups here, right? Is going to be the ester and hydrogen, right? Okay? And at this point, this is sometimes where it can become tricky, right? Because now what we have to do is we see this in 3 dimensions, and we have to sort of recognize what's on the same face of the molecule, what's on the appropriate sides of the molecule, right? And it's this carbon, I think, here that can often be tricky here, right? And the question from a certain standpoint is, if we sort of think about the big I over here, right? And that big I is going to be looking down and forming basically a cyclohexane, right? And when we draw that molecule, we're over here, right? And we're looking at it, right? Right? We have this carbon here is going to be this carbon here, and this carbon here is going to be this carbon here. So when we look at this one, I think we can tell pretty quickly which one we're going to be looking at first, right? Which one's going to be coming towards us, the proton or the ester, right? It's pretty obvious with this one, right? The proton is coming towards us, the ester is going away. But the challenge here, I think, visually can sometimes be this carbon here, right? Because what we need to do is we need to relax this bond. And which way are we going to rotate that bond when we relax it? Outside the ring, right? We're not going to rotate, we're not going to have this proton suddenly clash further into the ring. What we're going to do is we're going to rotate that molecule back a little bit. Everybody see that? We're relaxing it back. That means that the proton is my thumb, the amine is my finger, and as I rotate it back, right, proton's going to be coming towards us, the amine is going to be going back. You see that? You see that? See that? So the proton's coming towards us, the amine's going back. As we relax this system from the boat, the proton's now coming in the direction of the eye, and the amine is going away from the eye. Okay? So that's going to be the one possible product. The other possible product would be the enantiomer of that, where they're both coming towards you. Okay? Is that what you got? Okay. All right. Okay, so there's that one. Okay, other questions? Yeah.
Yeah, so this is from the sheet of the H2PO2 mechanism for the reduction of aerobizone results. Is that like a radical line or something else?
It's been a while since I thought about that. It's more, don't, for the sake of, I'm not going to ask a mechanism based on that one. In terms of the mechanism, I have to sketch it out. I believe, I have to think about that a little bit more again. I think that I don't remember. I remember looking into that last semester and it not being necessarily all that clear what the mechanism was on that case.
Remember, if you have the carbonyl portion is half in the form of radical, and then have a radical sort of on the, is that possible?
Yeah, we can sketch it out upstairs. Again, it's not, I'd have to look at it again. You're talking about the reduction of the N2 to the amine? Is that what you're talking about? Yeah, so.
You have N2 on the ring, you just have to, is that an
Oh, that one. Oh, not a reduction. Yeah. So that I think the best way to think about that, okay, the best way to think about that mechanism is that, again, consider it the nitrogen being a cationic leaving group, right? So think about it, the cation being left behind, and then, you can effectively break that molecule down if you want to and actually see like a hydride being formed. But that's sort of oversimplification of it, I think, as well. So I don't know right off the bat. I clearly completely even forgot that reaction. So, yeah, I don't know the mechanism of that. Okay, other questions? Yes. Synthesis. All right. Okay, so this is going to be the synthesis, but so there's trying to find something that might be interesting, and I was sort of thinking about Gil Mulder at the same time. The goal in this that I want you guys to think about that will spice this up, you could probably make it other ways, but what I would suggest you try to incorporate, which could be kind of a cool way to make this, right? Can you think of any interesting ways that you might be able to get to that compound there? Because if you get to that compound there, even if it's just for a short period of time, you have a little bit of ethylene in there, what'll happen? Kind of like a heterodyl Mulder, yeah. It's not an alderine. Alderine is when you have like an owl. Yeah, that's an owl. This is a heterodyl alder, I think, because it's got an oxygen in there. Yeah. Alderine is like this. It's like when you have an owl group, and this becomes your so the question is, can you guys think of a way to transform? You might be able to think of other ways to get there, but this could be cool. Like the question is, can you guys think of perhaps some type of a interesting way where you could transform benzene into this molecule here? Yeah.
Well, that's the step in the oxidation, right?
So because I didn't teach it, I'll tell you, you don't need to do like, this is technically an oxidation. You could do this in an oxidation method, but you could do it through more standard chemistry you guys work, elimination style chemistry. Well, let's hear it. To get to this?
No, I mean, if you cut this, you could technically go like zero like that. So like,
Well, the question is, let's think about the carbon bonds that we want to make. Right? We want to make a carbon-oxygen bond, and we want to make a carbon-carbon bond. And once we get those carbon-oxygen bonds, let's imagine, for example, just in terms of thinking about what we have, let's ask the question, do you guys think you could make that? Yes. How would you make that? So Friedel-Crafts alkylation, right? So you can make this using one. Well, would you start with Friedel-Crafts, you think? How do you guys know how to make phenol? You guys don't really know too many ways to make phenol. So you may want to start with phenol. Yeah, it might just be best to do the chlorination sodium hydroxide step, right? That nucleophilic benzyne, method that you guys learned to make phenol. That's probably one of the few ways that you could make phenol without having to have like a nitro group in there. So you probably want to start with that. Do you guys remember that reaction, the chlorination? Yeah, let's just visit it real quickly. Right, so what you could do, right, how do you make, you can make the chlorides, you guys, I'm sure can all do that, right? So how do you guys make chlorides? How do you make chlorobenzene? Yeah, some Lewis acid, so we can say aluminum trichloride. Okay, and then once you get here, this is that one that I said is like probably not going to be all that useful on more complex targets, but it could be useful if you're just trying to make phenol, right? And that's that you take this molecule and you pressurize the crap out of it, right? It's sodium hydroxide, right? And superheat, super pressure, right? Really hot, really pressurized, right? And that's the one that goes through the benzyne. So it does an elimination, that wacky elimination to generate the benzyne, which then reacts effectively with the water. Yeah, I guess it would probably be the alkoxide, yeah, or the phenoxide, I guess. But and then once you're here, right? Then can you do the now at this point? Can you do the Friedel-Crafts operation? Could, right? There could be other ways you could do it as well. What might be a problem here with the Friedel-Crafts operation? I think it would probably be fine, but let's pretend that we tried Friedel-Crafts operation, and instead of getting C operation, we got O operation. Right? Try to make it like a real lab, right? Like, we tried this, we're like, oh, it'll be no problem, we'll put the methyl group there. And then meanwhile, the bromomethane methylated that carbon. And we're like, oh. We could protect it, right? So that would be one option, we could protect it. What's that? And, right, okay, so great. So then I bulk this one up, and then suddenly it only goes here, right? So what else might we be able to do? BCC, PCC, well, yeah, did we, I'm pretty sure we learned that. I forgot to teach you guys. Salicylic acid. We treat it with a base and CO2? Did you guys have? Yeah, I teach it now. Yeah, I taught it last semester. Maybe I forgot. So if you have a, okay, so whatever, if I didn't teach it, apologies. But sodium hydroxide, it's in your book, that's why I say just to be safe, just know all the reactions in your book. Just to be safe, and more. Right? So what you do is you effectively, it's enolate chemistry. It's very enolate chemistry-ish in that you're sort of making an enolate, right? So formally what's happening here right? And then so again, this could be another way that we could imagine. Because again, we just want that carbon there, right? We said that we could put a methyl group there, but really we just want the carbon source there. Okay? So what if instead of being here, right, what if we had now CO2H? Well, one advantage here, right, might be that we could reduce it down, right, and give ourselves that handle. So what if we did an LAH reduction? We would then get the alcohol. Sorry, because I know we're running out of time. That could be one thing that we could do. So somebody suggested H2SO4 and heat. What might that might go right here. Why? Because it's not going to reduce. It's going to protonate this. It's going to leave, and then you'll shoot the electrons around there. You can imagine brominating it, right? So that's the idea, right? So we'll just stick with that because there's no time left. But the idea was, could you treat it with H2SO4 and heat? And maybe in the presence of ethylene gas, just to be safe, right? What might happen, right, is that you might get to that molecule there through a sort of so you can do this. This is actually, I don't know if you can do this with H2SO4, but you can definitely do it with, say, for example, what I was going to say was put a halogen there and then deprotonate it, and it might kick out the bromide. That's called like orthoquinone chemistry. All right. Okay. I'll see you guys. Well, I'll see some of you guys this afternoon. Again, I posted exam 2 and the answers to it, so you can practice that over spring break. But you got some time now. Yeah. So it's everything. So that's what it will be focused on. So the majority of the material will be on that. But again, be prepared for organic chemistry is cumulative stuff.